I think we will continue now with the first lecture, with the morning session today. I hope you had a good break. I hope you had already a lot of nice discussions together and get to know each other now a little bit. We will have now the second part of the morning session. Hopefully it's really only this hour, not longer, maybe a little bit shorter. And then also the lunch is already prepared. So everybody who listens to a lot of interesting things, of course, is also hungry afterwards, and you need some new energy then afterwards. Where to go? Let's say my favorite topic, and the topic there I'm coming from is indeed memory technologies. And to be honest, young scientists overall, also for studies, are mainly working on the so-called emerging memories at the moment, because to just say it, they are cool, it makes a lot of fun, there are a lot of things to develop and to engineer, because that's not the standard version. And you will have also, here in Dresden, a lot of developments, and on all universities which deal with microelectronics, emerging memories are really a really hot topic. That's why I want to continue with that now and give you a more detailed overview on the emerging memories. That means on memory concepts that don't rely on charges, but on a huge amount of different properties, and on a huge amount of different mechanisms how to store information in material. That's it somehow. You have material and you want to store information inside material. And what are the so-called immersion memories, which are also already, let's say, on the market in parts. So some of them are really in the market, and that is the so-called mainly the ReRAM technologies. You will find there's also ReRAM technology from TSMC. You have PCRAM as technology that is started in the market, and of course the MRAM technology. So also TSMC has own MRAM module as embedded memory. Also Global Foundries is quite far in having their productive embedded MRAM technology. So that are really the technologies that are already coming. I will have a closer look on the on the different kinds of memories afterwards. So I will not go through this diagram now with all these various variants, let's say. What I want to show you now is more this kind of diagram, which shows why we have so many different kinds of emerging memories. It's just because none of these memories you can claim to be the so-called universal memory. Every type of memory, every type of material stack just has its pros and cons. And you cannot have, or at least it will be like that also in the future, that you don't have this kind of really ideal, perfect, super memory somehow. So that's why there are so many different developments at the moment, and there will be, let's say, niches for all of these kinds of memories. What I want to show you with this diagram is a little bit what are the main parameters after which memories are rated. So what are the main requirements, what are the main parameters, properties of a memory. Of course, in general, it's the area. How small can you make your bit cell? If you can make more cells smaller, then of course you can store more information. That is clear. For example, how many states can you store in one single cell? So do you have only a 0 and a 1? Or could you have in your memory cell different kinds of states? Then it would be, of course, also great, because then you would have one bit cell, but it would be more memory cells, finally. The working voltage, of course, is important to know. Retention. Now I'm coming a little bit to words that you always hear. If somebody talks about memories with you, they are talking about retention, endurance, that are the main feature words that you hear. And retention just means if you store an information in a memory cell, how long will it stay there until it's just gone by itself? That is the so-called retention. And you want to have, of course, if you have a non-volatile memory, it should be endless retention, but that's not true. So every kind of material can lose its information. Also, we lose our information. You know that we forget something. That's natural. Then you have the second word that's really special for memories, and that you will hear always, and they always ask for. It's the so-called endurance. Endurance should be high. Endurance should be high. Endurance just means how often can you rewrite or restore an information in one single cell. So how long lasts your memory cell in bringing in new information in new. So you store, delete, store, delete, store, delete. That is just this information, and that gives you the endurance. And really big endurances is if you have 10 to the power of 12, 10 to the power of 13, then you have a real good endurance of this is the amount of how often you can rewrite an information into one single cell that you made. Of course, speed is a question. The memory window, always given memory window means if you have of course, you can only store, do you have the information in the memory cell or do you not have it in? But of course, the question is how, and then you have to measure it somehow. And the question is just how far are these states away from each other so that it's easy to measure it. So how much is the difference between, for example, a high resistance or a low resistance? If you say high resistance is a 1 and the low resistance is a 0, you need, a huge difference between them. Okay, always at the same time. The system don't want to work anymore. But I can just talk and wait until it's working again. So this difference between the states is really, really important. And one other word I will talk about later today also is the so-called CMOS compatibility. And that's mainly important for all these kinds of embedded memories. As I said, embedded memories are made inside or on top of a CMOS, of a transistor, and so they should not harm them. If you fabricate them on top of the logic, this fabrication and the materials you put in there should not harm your processor chip below. And that's just meant by CMOS compatibility. And you can see here, it's a comparison of the PC RAM, the ReRAM, and the MRAM, that they all have their highs and lows. So for example, MRAM really has a very high endurance, and the number of states is not very high, so that's why for neuromorphic computing it's a bit more difficult to use. You cannot use it for analog computing because you can only have 0 and 1, for example. And also the CMOS compatibility for MRAM is not that high, because you will see that later, you just have really crazy materials inside. So that's it somehow. On the other side, ReRAM, yes, has a high number of states, but for example, the endurance is not that good. So that is how I said the different memories all have different properties, and you will not have, for all the future applications and scaling, you will not have the universal memory. All of them have their way and their application. I will add today one additional emerging memory that is at the moment, at the border of coming to the market somehow. So a lot of big companies, also the big memory companies, had programs for this kind of memory, but it's not on the market now, but it's, let's say a little bit more mainstream. And I will add to the ReRAM, PCRAM, and MRAM, I will add the so-called, oh, sorry, that was wrong. Oh. Hey, I'm too fast. Okay, you see, some applications need small, lower speed. Now it's working perfect, thank you. I will also add the so-called FRAM here. As I said, the big companies have really huge R&D programs on that, but it's not in the market yet, but it's also a very, very promising memory that indeed the effect of being able to use this memory nowadays in an advanced CMOS lies on an invention that was done here in Dresden in 2006 to 2009. And that's why we here in Dresden like this memory, of course, and this effect, because it was somehow invented here in Dresden. Okay, at first, only one slide now, I will go through all these emerging memories. At first, the MRAM. What is the basic functionality of an MRAM memory? How does that work? Why is it a memory? You can see here the comparison between a so-called STT MRAM, spin torque. No, the name is gone, sorry. An STT MRAM and an SOT MRAM. The main important thing is, okay, here you can see how this kind of memory is built. What is the storage element? Here this looks quite simple. I will show you in a few seconds that it's not that simple. An MRAM is made of, let's say, 3 layers. At first here you have a so-called pinned layer, PL layer. In between you have a tunnel barrier, and on top you have a floating layer. All these layers are materials which can have a magnetization. So they have a distinct magnetization. And the pinned layer always have the magnetization in one direction. And the floating layer, so it's also sometimes called the reference layer. And the floating layer here, it's a material there you can change your magnetization. And at the end, it's quite simple. If, of course, this the material layer, the magnetization of this floating layer has the same direction like the pinned layer, you will be able to have a current flowing through this stack. If the floating layer has a magnetization in the contract, in the other direction you will not have any current flowing, and that's your 0 and 1. That's in general looks like it's simple, but of course at the end it will be not that simple. To write an information here, that means to tune this floating layer in this kind of configuration, the STT MRAM, you need a current that flows through this stack, and by this current you can somehow change the magnetization of the floating layer. Because this has some disadvantages, I will show you later. Also, a second kind of integration scheme is done or is studied. It's the so-called SOT MRAM, spin orbit torque MRAM. There you can program your floating layer, where you just can decide which direction of magnetization you have. This is done via a metal line on top. There your current is just flowing over this layer, and only by flowing over this layer you can somehow change the magnetization of your floating layer. I will go on to the advantages of this slide later. At first I want to show you, as I said, okay, here it looks quite simple, but at the end it's really not simple. To build such a kind of memory element, such a kind of memory stack, I show you here these TEM images of a real MTJ. MTJ is magnetic tunnel junction. This is just the name of this kind of material stack, of this kind of magnetic tunnel junction. And this is a really, really complex layer. So not only 3 layers, to be able that it is a pinned, a floating, and a tunnel barrier, you need up to 15 layers of thin materials, which are sometimes really in the angstrom level. So you really have to put angstrom level controlled layers on top of each other, that it really works. So you can see here one example on the right side. And the problem, if you now want to build this material as an embedded memory, you really have to achieve this high precision of the layers, and you have to achieve these properties under a very restricted back-end-of-line thermal budget. What does that mean? If you, as I said, if you want to embed the material on top of a CMOS, you are not allowed to harm the CMOS below. That means you can only fabricate at lower temperatures. And that sometimes is not good if you want to have a really well-defined and optimum material stack. So that is here the real challenge. But it's working, so a lot of good engineers find good solutions for this kind of memory, and it works quite well. And that's why you will find it as a TSMC technology. And as I promised now, some advantages for the future for this kind of stack integration. So this one is now really on the market. The STT MRAM is on the market. It's a more simple stack. An SOT MRAM would be the wish for the future. It's not on the market yet, although you would have really the advantage of an even higher endurance, although MRAM is already quite high in endurance, because you just change the magnetization of material, and that does not, let's say, this changing, writing and rewriting, changing the magnetization, just changing a spin does not harm material. So it's not so much stress to the material. That's why it has a high endurance. But if you even try to program this material not through the material stack, but just on top of it, of course, this would give you an even higher endurance, because you don't need to go through the stack. That's also the second advantage. If you don't need to bring the right current through a high resistance stack. So overall, I mean, it's a material stack, several materials. They are maybe not really conductive, so more high resistance, and you have to bring current through. That means you need a lot of power. That's energy to bring current through such a stack. If you just flow through a metal on top, you don't need so much power. That is the good thing for this kind of integration structure. So normally you would have the advantage of a lower write energy and also a higher write speed, that you can be really faster. But the big problem for this integration, you can see here. This is only one transistor, what you need below to control the voltage flowing and the programming and so on, and to control the readout. For this kind of SOT MRAM, you need 2 transistors, and that's just more area, more space, and that's the problem at the moment, that you cannot scale it so much, although you have a lot of other advantages. PCRAM, only shortly. It's not the most famous one now. Also in the around 2000 and the 2000s until 2005, a new kind of memory was developed, and here, what is the main finding was that you have a very special material system. In that case, that are the so-called chalcogenides. They can change their state, their physical state, just by applying heat. Of course, we all know that all materials somehow can change their state if you apply heat. If it's warm, you have water. If it's cold, it's ice. It's just quite simple principle. But here, of course, you need a material that can very fastly change its state and at temperatures that are somehow available. The phase change would be really happen at temperatures that are realistic for a microelectronic application. So you cannot near 1,000 degrees, or you're not cooling the material. You need something that is a typical temperature. And for that, really the chalcogenides are quite good. And here you can differ in the materials either between the crystalline state, and the crystalline state has a low resistance, so it's quite conductive, and you can have an amorphous state. This has a high resistance, so it's non-conductive. And just by heating, you can change this kind of state. So a writing would be heating up and and then cooling down again, you can have the second state. Typical materials, but now we are starting already with materials, and the thing that I told you before, CMOS compatibility and so on. Also, these materials that you can use here are not that easy. It's not only silicon dioxide, it's something really difficult and complex to be controlled also. So it's not the most easiest way. However, it's used. What are the advantages of this kind of memory? In general, it has really a good scalability, because for the material, it doesn't matter if it's large or small. You can already have this kind of phase change in a quite small area, and it will always work. So that is the good thing. I have a typing issue, I think. Yeah, cost competitive. I will change that later when you get the slides, so you can have all the slides. It's cost competitive, so yeah, it's just a capacitor. You have only a bottom electrode, one material, and a top electrode. It's not so difficult like 15 layers, something like the MRAM. And also in general, if you have high temperature applications, these things have really a good performance because the materials are quite stable then in the crystalline or in the amorphous form. Of course, limitations. I mean, if you want to switch something by temperature, it needs high power. There is some power consumption. And in general, that's just an additional information. You always have some retention issues for the high resistance state. So yeah, it starts with the amorphous phase. If it's not that perfect, also starts to be a little bit conductive with time. Last one from the really emergent memories that are on the market already. So we have also the ReRAM. That's also a very, very simple memory type, really simple. Also have just a capacitor, that means a bottom electrode, then your material and a top electrode. That's it. That's always the most easiest ones for the memories. And what's done here? Here you have a so-called resistive switching material. And the resistance you can, here in that case, switch by changing the voltage that is applied and the current to the memory cell, and then you can read the information at very low voltages. What does that mean? If you would have the memory cell, for example, at a high resistive state, so you can see here, if you increase the voltage, this memory has a very low current that is only going through. And you can measure this current, for example, and you would measure a very low current, then you know, okay, it's, for example, the 0. And if you have then switched the material in a very high resistive state, then you see, okay, if you then would measure the EV curve, you see, okay, you would have this kind of really high current that is flowing, so you know you are in the second state, in the low R. And the switching overall for these kinds of ReRAM types can be either bipolar or unipolar. That is always the main difference, or how you can distinguish different ReRAM technologies, because there are many options how to do that. And one possibility is, or what means unipolar switching, that means just that you can switch between for example here, from a high resistive stage, then you're coming to a distinct high voltage, then you switch your material and you will end up then at the lower resistive states here. And if you would now start again, you have now sweeping from 0 volt to a high volt, and you are now in the high resistive state. There is a distinct voltage already on this side. There you would switch back to your high resistive state. And that everything done on the same polarity. So all on one polarity. If you would use plus polarity and negative polarity, also both is possible. And for the bipolar switching, that is really the switching that is better to be used, because it's more reliable, and so that you can be really sure. that you have only one of the states. Bipolar just means that you have the switching from high resistive to low resistive only for one polarity, but if you are once now at the low resistive state, you have to sweep the complete capacitor in the complete different direction, so really in the other direction, in the negative polarity, and only in the negative polarity field, it would switch back to your high resistive stage. So that is just the thing, what's happening in general. You can scale these memories quite good because it's a very, very simple device, and you can make them very, very dense. Overview, as I said, both is possible. There are a lot of material combinations and mechanisms that will help you or that will bring a so-called resistive switching. One is, for example, the so-called CB-RAM, conductive bridge RAM. There you just have a base material and you really bring a kind of filament inside your stack, which is made of ions, for example, copper or silver as ions herein. And just by having the filament or cutting off the filament, you have a high or a low resistance state. Next version, which is more popular, are the so-called OXRAM versions. And here, maybe that is the most important one. Here you normally have a high K material. That means a dielectric like tantalum oxide, hafnium oxide, also other materials. Inside these materials, you are just somehow implementing oxygen vacancies inside, and either via these vacancies, you have also made a filament through the material, and either if you have this filament, you have a conduction, that means a low resistance, and if it's broken somehow on one interface, then of course you don't have any conduction anymore, and then you would have your high resistance state. And final version, just that you hear it, it's also this kind of CMOX, it's also possible. So a lot of different versions here. You have oxygen ions only at the interface, and they are moving from the electrode inside the material. And here you don't have a filament, but an interface that is either there or it's vanishing. And either you have the vacancies there, then it's your layer is the conduction is interrupted, or you don't have it there, then it's not interrupted. Okay, that was the overview on ReRAM technology. Now I'm coming to the ferroelectricity. I hope that I will be a little bit faster now. But yeah, it's always a lot of things to explain. What means ferroelectricity? There are a lot of ferroelectric materials, and what does it mean? It just means that in the crystal structure of a material, you have a polar axis that can have two stable states with a spontaneous polarization. What does that mean? I think this picture is quite nice here. If you're thinking at, okay, this is barium titanate, it could be also PCT and so on. This is the crystal structure, and you can have this, you can see here this titanium here in the middle. You can either have it in this direction, or sometimes it really switches and the titanium can move to this position, and then you would have a polarization in another direction. And because the titanium is either here or here, you have an internal field in this crystal structure. So you really have a voltage that is going over this structure because it's not symmetric. If you would have an additional titanium here, everything would be symmetrically, no internal field. But you only have this one element, and that's why you would have an asymmetry, and you will get here polarization. That means an electric field that you have there. And the nice thing is for these materials is that you can reversibly switch between the field in this direction and the field in this direction, and via this switching, it's kind of a memory if you have this direction or this direction of your electric field. But very important to know is, if you hear about ferroelectric memories, it never has something to do with iron, never. Never. It does not have to do something with iron. It's just this kind of effect. Maybe you saw this one if you have studies on materials before. The ferroelectrics are a very, very special kind of material system. You know that we have next to metals, semiconductors, dielectrics, so the isolators. And within the isolators that are the dielectric materials, you have some special ones inside. So the main part is always the ferroelectrics. Then maybe you heard already about piezoelectrics. They are pyroelectrics and also ferroelectrics. Ferroelectrics are the smallest part, but they are the most strongest because ferroelectrics are by definition also pyroelectrics. They have piezoelectric properties, and of course they are powerelectrics, but not in the other direction. If you once hear this, it's always working in this direction. So ferroelectrics are all, but on the other side, powerelectrics are only powerelectric, and then you have piezoelectrics. In this direction, it does not work. What are typical ferroelectric materials in the past, or the first ones there this effect was found out, are, for example, the barium titanates and lead zirconate titanates, also several polymers. But of course, all these materials you cannot integrate into CMOS, above all not polymers. That will be really difficult. So luckily, between 2006 and 2009, a PhD student at a memory company here in Dresden find out that our high-K metal gate material hafnium dioxide that you have in a CMOS is also ferroelectric. So this was a real big invention one of the PhD students made here in Dresden, because he found out if you dope hafnium oxide a little bit with zirconium or with silicon or something else, you can make it ferroelectric. And that was really, a good thing. And since then, ferroelectric memories are really under study. They started the developments because, of course, hafnium dioxide is a more suitable material like PCT, for example. It's CMOS and ROS compatible. Everybody in the microelectronic fields knows how to work with it because you have it in your gate dielectric. It's proven for manufacturing and it's highly scalable. Why is this the case? So why is hafnium oxide ferroelectric? Because that was not expected, really not expected. Because normally if you build this hafnium dioxide also in the gate, from 1 to 10 nanometers at the beginning, this material in thin films only has symmetric phases. So hafnium oxide, the crystal structure of hafnium oxide in a normal case is symmetric. So you would never have any polarization inside because it's only symmetric phases like monoclinic, tetragonal, and cubic. Which one of these phases occur if you make a 5 nanometer layer depends on how thick you make the layer, what is below, so it depends on the interface energies and so on. So which phase you will get if you grow this kind of material is really determined by the film thickness and the substrate, and can be a little bit tuned via temperature and doping. So these materials are not ferroelectric. So what happened? Why? What happened? Why could we say that it's ferroelectric? And indeed, hafnium oxide has. The student did some measurements and found out, okay, I have hafnium dioxide here that has this nice polarization curve, so you can switch between two states. What happened? Where does it come from? And he, of course, had a look into the literature and found out that hafnium dioxide has at really high pressures. If you would push a bulk material really, really high, hafnium dioxide can also have a crystalline phase that is non-centrosymmetric. This is called the orthorhombic phase. And somehow, not by wonder, but by a good engineering science, this kind of phase was stabilized in thin films, which are used for microelectronics. And yeah, the way how to stabilize this phase, this is non-central symmetric. There you can have this. There you can have really this kind of switching between two states. Was realized by confinement, by stress, or by doping the material. So it was really possible to have this material available at low pressures in a normal thin film at 10 nanometers in a normal CMOS process. Right, and yeah, then of course a lot of studies started starting from 2010. And a lot of students and a lot of companies tested, okay, which dopants probably would help to get this material ferroelectric. And you can see here what's the bunch of materials, what is possible. And probably it's interesting, I mean, you saw the 28 nanometer gate flow that I showed you, and in PMOS, one is in hafnium oxide with an aluminum, the other one is in hafnium oxide with an lanthanum. So that are really comparable materials. So that's why we think in future this is a really, really good type of memory that can be integrated easily and will come, yeah, also as one of the future memories. Of course, it always also has some problems. That's why it's not there yet, but it has a high chance of being successful. And that's the final slide for this kind of ferroelectric memory, because this one is can be integrated a little bit different than compared to just an ReRAM or just an MRAM. There you just have this kind of material stack in the back end of line. For the ferroelectric memory, you can also build a so-called FEFET. So that means you can directly use your transistor to make a memory out of it. That's also possible. If you just use your FEFET with the high K metal gate, then tune the material a little bit so that it's ferroelectric, then you don't have a logic transistor, but you have a FEFET, a memory transistor. So that is also working. Very good is that you don't have a so-called a non-destructive readout. That means if you read, your the information is still stored, and by that you can have a high endurance, finally. There are also other possibilities how to use this effect. You can see that here, that you probably don't put it to the transistor dielectric, but as a classical ReRAM technology or ReRAM architecture, you just put a small capacitor at the drain, for example, then it would be a ReRAM. So in the past, really, somebody used PCT, but it's not used anymore. It cannot be scaled. Or you can put it here also on the drain, on the gate, above the gate. Then there are really embedded memories, and here you can also build a memory out of it. But here you always have a little bit the problem that you have a destructive readout. So endurance is not that good, but it's improved. You can do a lot of things. Okay, that is some overview to what's going on with regard to memories, which technologies are looked for. And at the beginning, I showed you the logic ones. Now I want to come to the field where are these microelectronics, where are the chips made. So a short overview again on clean rooms. Why do we need clean rooms to build memories and logic? And what about contamination management? If you're talking about so many different kinds of materials, what is necessary to be aware of? And clean rooms. I guess you already heard about it. Oh yeah, you already know that. What's a clean room? Why do we need a clean room to build microelectronics? So in general, it's all about particles. You don't want particles inside or on top of your microchip. That's why you need clean rooms, which are a room with defined temperature, humidity, it's also very important, and airflow, and in which the quantity and size of particles are controlled, really in order to limit contamination. How can you achieve this? So you always have a pre-treatment of the fresh air so that you have a distinct humidity and temperature. Then you are filtering the air via so-called HEPA filters, high efficiency particulate air filters, and only through these filters, via distinct filter fan units, the air is going into the clean room. There normally you have a so-called laminar flow of air, so that really everything, it's not turbulent and the particles can go everywhere, but that you really have a very controlled way of particles so that they are going only to the floor, and I think that's missing here in this, and the floor will always be open so that the air can go through the floor, of course. The air moves in cycles. You need to recool also all the dissipated heat that is generated by the machines. And one very important thing, I think you will see that if you have a look into the clean rooms also today, is really a concept for clothing and your own behavior. That means running is extremely forbidden in a clean room, because then you would have a lot of particles that we as humans are bringing. And of course, one thing is really, because that's also called clean room. So cleaning is also very important. So otherwise it would not work. Just as an information, maybe you heard that before, the classifications of clean rooms. So normally they are classified here in Germany. You normally classify via the ISO classifications. So you talk about these ones here. A real front-end clean room that you will see today also, I think, from the side. And also the CMOS clean rooms are an ISO 3. That would mean in US declaration would be a class 1. And in main part of the gray rooms, or also the 300 millimeter gray room, clean rooms overall are more an ISO 6, that would be the class 1000. And here you can see the specifications that are allowed in these clean rooms from particle sizes. So this amount of this size, and the bigger ones, even less particles are allowed in the clean room. So in this clean class 1, it's really strict that you, for example, only have 237 particles that are between 0.1 and between 0.2 and 0.3 micrometers. That is only allowed. I've brought you some numbers just to understand how many particles you would have in a town. So town air would mean roughly 10 to the power of 12 particles per square meters. That would be an ISO 12, something here. There you have 1 trillion if you would put together all these particles next to each other. If you would think about a 0.1 micrometer sized particle, that would mean 100 kilometers. If you go to the mountains, it's, of course, the air is already cleaner. That would be 10 to the power of 9. So that would be at least an ISO 9. You can start doing a little bit of electronic work, I think, in the mountains. that is possible. And the particle size of an ISO 3, that means class 1, or I don't know if you will see that. I hope you will see that. Otherwise, I will have to ask the colleagues if they bring one from my clean room to you. At 300 millimeter wafer size, not the whole clean room is an ISO 3, but the wafers are put in so-called FOUPs, front open unified ports. And here inside the FOUP, there you really have this ISO 3 contamination. And if you put together only these particles, 10 to the power of 3 times 0.1, that would be 0.1 millimeter, and that is roughly the size of the human hair. And as we are talking now about human hair, that's really important. What is the main source of contamination in a clean room is the human. You can see here 30 to 40%. So that's really why there should be a low amount of humans in a clean room. And of course, we have the clothing concept. And I guess everybody of you already saw these kinds of pictures where you have a microelektronik chip and a human hair incising together. So that would really harm all your microelektronik devices. You can see here that is only the interconnect version. You would even think that a transistor below would be even smaller. But particles are not the only thing. I told you that with all these emerging memories, you have a huge amount of materials in your microchip. And a big thing that is also really extremely controlled in clean rooms are the so-called material contaminations. So it's really important that the materials, for example, you want to use for the transistor are only there. You put it in the transistor, and that the materials that you want to use for an interconnect is not at the place there the transistor is. And you can only achieve this via a very, very strict, let's say, contamination management and thinking about how materials are behaving inside a chip. That is really important. And all the materials, so the complete chemical, the group of chemicals that you know, are for this somehow classified to see how is their influence on a microelectronic chip. And the first factor, how you can classify material, is the so-called D factor, the device or detrimental effect. And this always describes you how severe would be the influence on the function of a microelectronic device. So how severe is if you would have one gold atom in your transistor channel. Of course, that's not nice to have it there. The second factor is the so-called the X factor. It's the cross-contamination. That means what could be the potential distribution ways, how materials that you don't want are coming to the place there you don't want them. And that means that you have to learn about diffusion behavior, temperature behavior of single materials, and that you somehow classify different elements after this kind of cross-contamination potential. And the last factor that you classify your material is the so-called C factor, controllability, control methods. That means how easy is it to analyze this material and to clean the material. Analyzing is the really most important thing, because if you don't know that you have the material, you cannot control it, you cannot do any measures, you cannot do something against it. So the main important thing is that you can measure it. Even if it's there, it's okay. As long as you can measure it, you can do something against it. That is the main thing. Just an overview on how fabs are built. So all the fabs around here in the world, they have a material contamination management. They classify the complete PSE. And so you can see here, of course, you have, for example, a contamination class 1. So all materials which have a low influence on a transistor, which have a low risk of diffusion because they are stable materials and they stay there they are. And you can really measure them very well. They are together in this kind of group 1, Cl1. For example, hafnium oxide. The tinitride that I told you belongs to this class. And then, of course, it really goes up to materials. For example, class 3 is very important. This is material where you have a significant influence, also a very significant risk that, for example, the copper will move somewhere else because copper is very diffusive. It wants to go everywhere. And but the good thing is you can detect it quite well, so you can develop measures how to cope with this material. And here just an example, for example. That's great. This is just an example for a specification list, which amount of materials are allowed in the distinct classes if you measure it. And this is the example of the 300 millimeter research clean room of Fraunhofer IPMS. So also we have very strict rules for everything. Everything is specified. If we would measure on a wafer in a tool some values here that are not in the spec, you would open the tools, you would clean everything, and several times you stop the production, you stop everything, and really try to get rid of the material inside a tool. I will shorten this a little bit. Yes, because it's already over. I said that it's necessary to measure. Measuring metal contamination you are normally doing via vapor phase ICPMS, VPD ICPMS. So you really use wafers, you try to mobilize ions on the wafer, then you scan with a droplet, and this droplet of materials that you collect from your wafer are then analyzed in an ICP. Maybe just that to see this. So here you have this kind of vapor phase. There which makes a kind of vapor on the wafer. There you mobilize all your ions that you want to measure. Then you have this nice droplet that scans all your elements, and then you can measure it via this ICPMS. I will not go on to detail in ICPMS. The important thing is we have our own laboratory to do that, to really have a very, very continuous qualification of the clean room. So even if you have a research clean room, it's necessary to measure all the contaminations, because otherwise our devices that we develop will not work. Just a short look. Maybe I will skip that a little bit. That's just a look into the CMOS cleanroom that you, research cleanroom that you will probably not see during the camp, because we cannot go to all our sites that we have at IPMS. That is the view inside a 300 millimeter cleanroom. As I said, all the wafers are in these nice FOUPs here. But here in Dresden, we have some of the largest research clean rooms for front end that we have here. And the main thing is that you really need industry-grade equipment so that you can really have the high quality of devices that you're making, and that you need this kind of, very professional contamination management. Okay, and by that, I will have now, it's the last and smallest part of the lecture of the morning. This is the end there. Then Jörg Amelung will continue in the afternoon via discussing all the single semiconductor processes that are needed to build a CMOS, that are needed to build memories, that are needed then to build MEMS, and so on. It's really a huge amount of different processes that are necessary to build at the end such a kind of complex chip that I showed also in the morning. You have a huge amount of different deposition methods, which have a lot of different properties that you need to tune special applications. You need, of course, the complete patterning so that you make structures somewhere, the lithography, then the etching to really etch feature sizes in a thin film, and then you have also some processes that are needed to tune special material properties. That's, for example, the implantation and annealing. I will today focus on one very, very special semiconductor process, which is necessary to, let's say, or which is somehow the key process for advanced and future CMOS and memory. And that's the process that defines the, let's say, the active layer, the active calculating layer, the active memory element, and that is the so-called atomic layer deposition. Atomic layer deposition, this invention was really important to be able to deposit all the high-K dielectrics for all of our transistor logic and the high-K materials that are used for all, or for the main part of our memory devices. So for all the ReRAM, PCRAM, ferroelectric RAM, they are only possible mainly if you're using ALD, atomic layer deposition. That's why I want to give you a short excursion on this semiconductor process that is most advanced and most developed only on 300 millimeter. It's available, of course, also on 200 millimeter, but the most advanced processes are only available on 300 millimeter. What's atomic layer deposition? Overall, it's a chemical vapor deposition, and which is based on sequential gas-solid reactions. So you really need a chemisorption, a chemical reaction of a precursor that is coming in with your surface. That's it somehow. But the special thing about atomic layer deposition is that you want to have a material that you're doing the different parts of the material really in a sequential phase and alternately. You don't put everything together at once and that you have a reaction in a reaction chamber and then everything somehow drops to the surface. You do everything sequentially and really have, let's say, saturating surface reactions. Step by step. You can really go very step by step, depositing material. At first the metal, then you want to have, if you want to have a dielectric, it's hafnium dioxide. So at first you deposit the hafnium and then you oxidize it. Then you have the hafnium again and then you oxidize it. And that's really this very, very sequential and alternating way. What is it good for? Mainly it's good for to have really, really conformal material layers. Conformal, that means it can be deposited on all kinds of feature sizes. I showed you in the morning this fork size and nanosheets. ALD is the only method which can really nicely deposit around these structures. And next, also, you have a very, very fine thickness control down to the nanometer range because everything is done sequentially. So that's only possible with ALD. You can have a digital stoichiometry control. If you want to mix something, you can also do that very, let's say, sequentially, but always digital. That means you have, for example, you build hafnium dioxide and you dope it with a silicon. You have a first hafnium dioxide layer. Then you have one pulse of silicon inside, and it's always the same amount. If you do a second pulse, you have the same amount again on top, but nothing in between. You cannot have half pulses or half amounts of layers. You will always have the same amount that you put on top. That's why it's a kind of digital stoichiometry control. And you can, of course, and that's shown here, nicely also deposit in very, very deep structures. So you can have it so-called a high step coverage with this kind of project. Here it's an example for zirconium dioxide, which is used for DRAM applications, DRAM capacitors. As I said, it's sequential, so I plotted this here again. What does that mean, the ALD reaction cycle? So at first you have your substrate here. That's the example for an hafnium dioxide process used in all CMOS and ferroelectric memories. You have your substrate. Then you bring to the substrate in your chamber or over the substrate, you bring a first reactant called reactant A. In the case of hafnium oxide, it would be a so-called tema hafnium. That means a special chemical which has hafnium inside and some organics around. And this is reacting with the surface and really reacting and giving some byproducts. Then you have the second step. This means it's a kind of purge. There you purge all the precursor or all the reactant A out of the chamber that is not used because it's only, you have only the reaction on the surface and also the byproducts are purged away. And only if it's completely clean, if your chamber is completely clean, you bring in a second reactant B. If you want to deposit hafnium oxide, it could be an oxidizer, it could be ozone, for example. Then you have the ozone. The ozone reacts with the surface and makes hafnium dioxide out of your hafnium with some organics at the beginning. Then you have hafnium dioxide here on top, again some byproducts. And then you have the next step is again a purge. There your reaction chamber is cleaned. Everything out. You have only your surface with hafnium dioxide. And then you can start the next cycle here again, bring reactant A again, and then it gives you the next layer of hafnium and then the oxidizing again. That is how it's working. Sometimes just for naming, half of the part is sometimes called half reaction. The factors that causes this nice deposition that you only have one layer on top. There are several factors that cause this kind of saturation, that you only have this one layer. The first thing is that this process relies on chemisorption. Chemisorption means that you have a real chemical reaction between the surface and the reactant. And you don't have any chemical reaction between the reactant molecules that are in the chamber. So they only react on the surface. That is the big thing. Of course, you need special chemistry that is doing this, only this. Second thing is that you really have the separated reaction pulses so that you don't have an uncontrolled reaction between the oxygen or ozone and your metal precursor, for example. Sometimes, so you have a distinct amount of material that you can deposit on a surface, and this amount can be also controlled via the so-called steric hindrance of ligands. Now we are really deep in the chemistry. And what does that mean? If you have a chemical molecule that is coming to the surface, it wants to react, but it's bulky and large. And it's on the surface, and maybe a second one is coming. It will sit next to it, but probably there would have been more reaction sites on the substrate below this bulky material, and they are just not filled. That is just the thing. What you always have only a distinct amount of material on top of the surface of the substrate due to the size of your reactant molecules. And of course, in general, also the growth or how much material you can bring on a first surface also relies on the amount of reactive surface sites you have on your substrate. Some of the substrates have maybe not so much surface sites, and some of them have more reactive surface sites. I have here only one example for you for such a simple deposition of zirconium dioxide on different substrates. And you can see here on silicon oxide, it's this curve, saturation curve. That means saturation curve means you bring material inside a reaction chamber only for 1 second, or you leave it in the chamber, for example, for 6 seconds. And if you have a saturation, that would mean you have only one layer on the surface, but you will bring not more layers on top. Doesn't matter how much material you have in your chamber, and that's really the case here. So it doesn't matter how long you have material inside the chamber, the growth rate is not increasing. You only have one small layer on top. But here you can see that this can differ if you have different substrate. This is the line for silicon oxide. This is the line for titanium nitride, which is a rougher material, higher surface area, so you can deposit more material. I think that's somehow the last slide. I've brought you a little bit to have a feeling on which kind of precursor types, chemicals you can use for this ALD, or what you have to think of if you're coming now from the material side, if you are maybe a material supplier. Precursors for ALD should be very volatile, they should be very stable, they should be very reactive, they should have a reaction temperature that is realistic, and of course they should have a high growth rate. So everything the best together. Of course, that's difficult. What are typical precursors? You can either have for the metals, if you want to have hafnium dioxide, that's all possible options now to make hafnium dioxide. You can have it as an inorganic version, so-called halides that you have here, your hafnium, for example. This is connected to a fluorine or a chloride, that would be the halides. They are nicely used for high-K metal gate mainly, so that is the main for the high-K metal gate deposition. If you want a planar one, then they are really good. They are reacting quite nice with water only. So that is of course better than making ozone, just from the green point of view. Then you can have various amounts of organics, metal organics. I don't know who of you ever had a lecture on organic chemistry. Then you will see that it's really a large field, and you can do a lot of things there. So you have the organometallics there. The hafnium is directly connected to a carbon. Then you can have alkoxides there next to the metal. You at first have an oxygen, and then all your organic carbon and hydrogen parts of the molecules are coming. Or you can also use alkylamides. There you have a nitrogen next to the metal first, and then you have your organic ends and so on. So there is a huge amount of possibilities, and that's also a big business. developing new precursors, then looking on the on the green aspects of these single precursors, but at the same time they should work, and they should work, and they should let's say work in the different structures and so on. Just to be complete, the non-metal precursors that you can use. The best would be, of course, always to use water. That is the greenest version. But sometimes, of course, these kinds of materials only react with ozone. That is the problem if you want to have reactive things. And I think I will skip that because you are all hungry, or just to show what is the temperature window, the so-called temperature window of an ALD process. The special feature is, the only thing I want to show you here is that only at distinct temperatures that you have to develop, you will have this kind of saturation and this real stable growth rate. And this temperature window is different for every precursor. So if you want to have a new precursor, you have to identify, oh, what's my reaction window? That is the first thing what you're doing as an engineer. And due to the time, I will not explain you what can happen out of the ALD window. There can happen a lot of things out of the ideal process window. I will not look on that because of the time. And I think, with this next view, or the last view on semiconductor processes and how difficult they are, how complex they are, I would finish this first session of the morning. I hope I could give you some input on microelectronics in general, and then the focus more on the logic and the memories. That would be the scaled, the more advanced technologies. And as we are on these small feature sizes, then of course I hand over to the clean rooms and the contamination management. That is very important to produce all these kinds of microelectronic chips. And finally, a first impression of how difficult and complex this single semiconductor process is. So every single step could be to build finally a microchip. So with that, I want to say thank you. Thanks for your attention for such a long time. And now, of course, I want to wish you a very good lunch break. Good hunger. Thank you.